Right now, while you're watching this, billions of organisms are doing something extraordinary inside your compost pile. And I mean billions. They're eating, reproducing, and generating so much heat that the center of your pile could be hotter than a cup of coffee. Most gardeners build a compost pile, toss in their scraps, and kind of forget about it. But what's actually happening in there, especially overnight, when everything goes quiet? It's one of the most fascinating biological processes in all of nature. And once you understand the science of composting, you'll never look at your compost the same way again. Let me show you what's really going on. The moment you build a compost pile, the clock starts ticking. Those fresh kitchen scraps, those grass clippings, the shredded leaves, they're already covered in bacteria. Millions of them per gram, just sitting on the surface of every leaf and every apple core, waiting for the right conditions. And when you pile all that organic matter together and get the moisture right, those bacteria wake up and start feeding on the easy stuff first. Simple sugars, amino acids, starches. The buffet is open. Here's where it gets wild. Under the right conditions, these mesophilic bacteria can double their population every 20 to 30 minutes. Think about that. One single bacterium could theoretically become over 1 billion in just 10 hours. Now, compost conditions slow that down a bit, but we're still talking about an absolutely explosive population boom happening inside your pile. And as they eat and reproduce, they generate heat, not from some chemical reaction you added, from their own metabolism. It's the same basic process your body uses to stay warm. Aerobic respiration. The bacteria consume carbon compounds and oxygen and release carbon dioxide, water, and energy. About 55% of that energy escapes as heat straight into the pile. This is why, within 17 to 24 hours of building a properly balanced pile, the internal temperature can shoot past 120 degrees Fahrenheit. By 48 hours, you could be looking at 140 to 160 degrees at the core. And here's the part that always gets me. While the center of your pile is pushing 150 degrees, the outer 6 inches might be close to whatever the air temperature is outside. On a cold winter morning, you could have an 80 to 100 degree temperature difference between the core and the edge. That's just incredible. That steam you see rising from your compost on a cold morning, that's not smoke. That's not a fire. That's water vapor from the hot, moist interior condensing when it hits the cold air. Same physics as seeing your breath on a chilly day. And it's actually a sign that everything is working exactly as it should. But here's what most people don't realize. This first wave of bacteria is just the opening act. What happens next is a full-blown relay race with 4 distinct stages, and each team of organisms unlocks something the previous team couldn't touch. Those mesophilic bacteria I just mentioned, they handle stage 1. They thrive between 50 and 108 degrees Fahrenheit, and they chew through all the easy food in a matter of hours to a few days. But as their own metabolic heat pushes the pile above 104 degrees, they actually cook themselves out of a job. That's when stage 2 kicks in. Thermophilic bacteria were already sitting in your pile the whole time, dormant, waiting. Some of them exist as heat-resistant endospores, basically tiny survival capsules. And as the temperature crosses that 113-degree threshold, they wake up and take over. These thermophilic organisms are the heavy lifters. Bacteria like Bacillus species and members of the Firmicutes phylum dominate this stage, breaking down proteins, fats, and complex carbohydrates like cellulose and hemicellulose, the structural molecules in plant cell walls, things the first wave of bacteria couldn't even touch. And because chemical reaction rates roughly double with every 18-degree Fahrenheit increase, decomposition at 140 degrees is happening 32 times faster than it would at 50 degrees. But even the thermophiles have their limits. Most of them die above 158 degrees, and as they consume all the high-energy compounds, the metabolism slows, the heat fades, and the temperature drops. That's when stage 3 begins, and this is one of my favorite parts. As the pile cools below about 104 degrees, fungi move in. You've probably seen this. Those beautiful white threads of mycelium spreading through your compost. That's not mold going wrong. That's your pile working perfectly. Fungi like trichoderma and phanerocate chrysosporium can do something. Almost no bacteria can. They can break down lignin. Lignin is the tough, rigid polymer that gives wood its structure. It's essentially nature's plastic. And it's so resistant to decomposition that it actually increases in concentration during composting because everything else gets consumed first. Only certain fungi, called white rot fungi, have the enzymes to completely dismantle lignin and turn it into carbon dioxide. Here's a fun fact. If you inoculate your pile with cellulolytic fungi like aspergillus and trichoderma, you can accelerate composting to as little as 1 month. Then comes stage 4, actinomycetes. They look like gray spider webs spreading through the outer layers of your pile, and most people mistake them for fungal growth. But they're actually filamentous bacteria. They tackle the most resistant compounds left behind: woody stems, bark, even chitin from insect shells. And actinomycetes are responsible for something you've definitely noticed. That incredible earthy smell of finished compost. That comes from a single molecule called geosmin. It's produced primarily by a genus called Streptomyces, and humans can detect it at 5 parts per trillion. That's one of the most potent scent compounds we know of. It's also the molecule behind petrichor, the smell of rain hitting dry ground. So when you bury your nose in a handful of finished compost and breathe in that earthy aroma, you're smelling a molecule whose genetic blueprint traces back roughly 3 billion years. Now, all of this biology only works if you give these organisms what they need. And the most important factor, the one that makes or breaks your compost, is the carbon to nitrogen ratio. The ideal ratio is about 30 parts carbon to 1 part nitrogen by weight. And the reason is beautifully simple. Microorganisms themselves have a carbon to nitrogen ratio of about 8 to 1 in their cell bodies. They need carbon for energy and nitrogen for building proteins. But for every unit of carbon they incorporate into new cells, they burn roughly 2/3 as fuel. So they need about 3 times more carbon than nitrogen. The 30 to 1 ratio accounts for the fact that not all carbon in your pile is equally accessible. When you get it wrong, the symptoms are obvious. Too much carbon, say a pile that's mostly sawdust at 325 to 1, and the bacteria simply can't find enough nitrogen to reproduce. The pile stays cold. Composting takes months or even years. Too much nitrogen, like a pile of pure grass clippings, and the excess nitrogen escapes as ammonia gas. That sharp, pungent smell coming from your pile, that's nitrogen literally evaporating into the air. Studies show you can lose 16 to 74% of your total nitrogen this way. And speaking of grass clippings, here's something most gardeners don't think about. Grass clippings are about 80 to 85% water. Those flat blades stack together and seal like wet paper, creating an impermeable layer that blocks oxygen completely. Within days, the clippings go anaerobic, and that's where the real problems start. Which brings me to oxygen, the unsung hero of composting. Aerobic respiration produces about 38 units of cellular energy per glucose molecule. anaerobic fermentation, just 2. That makes aerobic decomposition roughly 15 to 19 times more efficient. Without oxygen, your pile doesn't just slow down. It shifts to a completely different kind of decomposition that produces methane, hydrogen sulfide, which is that rotten egg smell, and a whole cocktail of foul-smelling compounds. This is why turning your compost matters so much. If you're finding this useful, do me a favor and hit subscribe. I cover the science behind better gardening every week. Now let's talk about the smartest composting method ever developed. Professor Robert Robb at the University of California, Berkeley developed what's known as the Berkeley hot composting method, and it can produce finished compost in as little as 18 days. The protocol is specific. Shred everything to 1/2 inch to 1.5 inch pieces. Mix greens and browns to a 30-to-1 ratio. Build the pile at least 3 feet by 3 feet by 3 feet. Get moisture to about 50%, like a wrung-out sponge. Then turn it every other day, starting on day 4. The key insight is that when you turn a pile and fresh oxygen floods the depleted zones, it triggers an immediate explosion of microbial activity. A cooled pile can show a brand new temperature peak within hours of turning. And here's how you know when active composting is done. When turning no longer causes a temperature spike, the process has shifted to curing. That's your signal. But can you turn too often? Actually, yes. Excessive turning causes moisture loss, increases nitrogen loss through ammonia volatilization, and can prevent the pile from ever reaching thermophilic temperatures. You can literally turn your nitrogen into thin air. Now, that thermophilic heat I mentioned earlier, it's not just speeding up decomposition, it's destroying things you definitely don't want in your garden. Weed seeds. Fresh dairy manure contains an average of 75,000 seeds per ton. At 140 degrees Fahrenheit sustained for 3 days, you kill 90 to 98% of most weed species. But even at 98%, that's still 1,500 viable seeds per ton. Some weeds are incredibly tough. Tumble pigweed needs over 100 hours at 122 degrees to reach 90% kill rate. Pathogens like Salmonella and E. coli are destroyed when the pile maintains 131 degrees for at least 3 consecutive days. And finished compost doesn't just avoid disease, it actively suppresses it. Research has shown that 54% of all tested compost pathogen combinations showed significant disease suppression. Compost essentially vaccinates your plants through something called induced systemic resistance. But there's one thing composting cannot destroy, and this is critical for every gardener to know. Persistent herbicides like aminopyralid, clopyralid, and pecloram. These synthetic chemicals survive animal digestion, pass through livestock manure completely unchanged, and do not break down during composting. Their half-life is 1 to 2 years. Full degradation takes 2 to 5 years, and concentrations as low as 1 part per billion can kill sensitive plants like tomatoes, peas, and beans. That's 1 drop of water in an Olympic swimming pool. If you're bringing in outside manure or hay, always run a bioassay first. Mix the suspect material with clean potting soil. Plant some peas or beans and watch for 3 to 4 weeks. Cupped or curled leaves mean contamination. So what do you actually end up with after all this microbial effort? Something genuinely extraordinary. A single teaspoon of finished compost contains 100 million to 1 billion bacteria, up to 900 feet of fungal hyphae, 10,000 to 50,000 protozoa, and up to 300 nematodes. There are more living organisms in that teaspoon than there are people on Earth. The stable organic matter that forms, called humus, can hold up to 20 times its weight in water and dramatically increases the soil's cation exchange capacity. Every 1% increase in soil organic matter helps your soil hold an additional 20,000 gallons of water per acre. In sandy soil, adding a 3-inch compost layer and tilling it into the top 6 inches can increase water holding capacity 2.5 times. And unlike synthetic fertilizers, compost releases nutrients slowly. Over 90% of the nitrogen in finished compost is in organic form, meaning only 10 to 30% becomes available in the first growing season. The rest releases gradually over subsequent years. This makes it virtually impossible to burn your plants with compost. You just cannot over-apply it the way you can with synthetic fertilizer. Before I wrap up, let me quickly hit the mistakes I see most often. The number one reason most home piles never get hot is simply that they're too small. The minimum is 3 feet by 3 feet by 3 feet. Below that, heat escapes faster than microbes can produce it. Second, those commercial compost activators you see at the garden center? Save your money. Multiple studies have tested them and found no improvement over simply using a handful of finished compost or fresh grass clippings as a starter. The microbes are already on your materials. They don't need a special product to get going. And third, please stop adding shovelfuls of garden soil to your pile. Soil displaces organic matter without meaningful benefit. A tiny handful of finished compost is a far better inoculant than half a wheelbarrow of dirt. Now, I want to leave you with a few facts that completely changed how I think about composting. Archaeologists have found evidence of composting in Scotland, dating back 12,000 years. Stone Age farmers were planting directly into compost heaps. Cleopatra made earthworms protected under Egyptian law, and exporting them was punishable by death. And a French inventor named Jean Pain produced 100% of his household energy from compost in the 1970s. He heated his home, cooked his meals, and even powered his truck using hot water piped through a massive 50-ton wood chip pile. That pile provided hot water at 140 degrees for 18 straight months. Your compost pile is not a pile of rotting garbage. It's a biological reactor, a microscopic ecosystem, and one of the most elegant recycling systems on the planet. Every time you add a handful of kitchen scraps or a bucket of shredded leaves, you're feeding billions of organisms that are manufacturing the most valuable substance a gardener can own. If you want to see how to build a pile that actually reaches thermophilic temperatures, I've got a step-by-step video on screen right now. Click it, and I'll walk you through the whole process.